Pascal's identity is defined as n plus 1 choose k equals n choose k minus 1 plus n choose k, where n choose k is a binomial coefficient. Two common ways to prove this theorem are combinatorial proof and algebraic manipulation. We will use a combinatorial proof here. For easier notation, we will use the form n minus 1 choose k plus n minus 1 choose k minus 1 equals n choose k, for 1 is less than or equal to k, which is less than or equal to n. First, we must establish that n choose k counts how many ways to get a k subset out from a set with n elements. Let us choose a particular element e from the set n elements. This way, e either belong to the k elements chosen for the subset or not. In the event that e is in the subset, the next step is to choose k minus 1 more objects from the remaining n minus 1 objects. We can do this because we know that e will be in the subset. We say n minus 1 choose k minus 1 to do this. If e is not in the subset, then you must take n minus 1 choose k.
Pascal's identity is interesting in that it can be used to recursively define binomial coefficients. This recursive definition is useful in the computation of binomial coefficients because only addition and not multiplication of integers is needed to use this recursive definition. However, the recursive nature of Pascal's identity forms the shape of a triangle, which is what we can define as Pascal's triangle. Pascal's identity shows that when two adjacent binomial coefficients in this triangle are added, the binomial coefficient in the next row between these two coefficients is produced. As you see in the left, as the left triangle shows you, two identities in the line preceding the following line, so 6 choose 4 plus 6 choose 5, yields you the coefficient in the next step of the binomial. This recursive definition generates the form of a triangle and is very useful in calculating binomial coefficients. Now let's use an example. Let's have an example using Pascal's triangle. Imagine you have 5 books. Let us imagine that you wanted to read one. How many ways are there of selecting a single book? Well, that's easy. There are 5 ways. If we label the books A, B, C, D, and E, we can choose any one of the 5 different selections. How many selections are there if we wanted to select 2 books? Well, let's list all of the combinations. AB, AC, AD, AE, BC, BD, BE, CD, CE, and D. That makes 10 selections. What about if we wanted 3 from 5? Well, that's easy. Picking 3 from 5 is the same as discarding 2 from 5. So there are 10 ways of doing this. Picking 4 from 5 is the same sort of idea as discarding 1 from 5, so 5 ways. Of course, if you want to select all 5 books, there's only one way of doing that. There's also just one way of selecting no books. So tabulating what we have, we see that the number of selections from 5 is 0, 1, 2, 3, 4, and 5. And the number of ways of making these selections corresponding to each selection respectively, in this table that we show you, is 1, 5, 10, 10, 5, and 1. Well, that looks surprisingly close to Pascal's triangle. So, this is a fascinating aspect of mathematics that two seemingly unconnected topics are in fact connected. In this case, we have connected between algebraic expressions and selections in combinatorics. The number of ways of selecting R objects from a total of n is written as n combination R, where n is the exponential subscript and R is the lower subscript. So the above selections can be written mathematically as follows. There's one way to select no books from 5. 5 choose 0, which equals 1. There are 5 ways of selecting 1 book from 5, so 5 choose 1 equals 5. There are 10 ways of selecting 2 books from 5, so 5 choose 2 equals 10. There are 10 ways of selecting 3 books from 5, so 5 choose 3 equals 10. There are 5 ways of selecting 4 books from 5, So 5 choose 4 equals 5. And there is only one way to select 5 books from 5. So it's 5 choose 5 equals 1. Thus we can see the practicality of Pascal's triangle in simple combinatorics. We can also expound upon it and make our lives easier when we try and simplify binomial expressions which are very long. For instance, if you had x plus y to the 100th power, the only way you could really simplify that quickly, is if you use Pascal's triangle. That's the power of the triangle.